Okay, so hello everybody, and thank you very much for joining in today. I will talk about a paper called SVFR, a Unified Framework for Generalized Video Face Restoration. So as you can probably already guess, this is about a model created for video face restoration tasks. And so let me maybe start by talking a little bit about face restoration in general. So the task of face restoration, or short FR, describes the process of enhancing and recovering degraded images of human faces, oftentimes under exploitation of artificial intelligence techniques, such as it will also be the case here today. The goals are typically to fix problems such as low quality, noise, blur, or also aging effects. And of course, there are many useful applications of face restoration. For example, obviously, restoration of old photos, but also, for example, surveillance image enhancement. So, yeah, imagine, for example, you have a surveillance camera and the camera records some crime. And of course, you want to identify the person who committed the crime. So, you take a look at the footage, but then you might notice that the footage is actually of quite low quality, so you cannot really recognize the face. And then you might apply such a technique to improve the quality and to be able to actually see the face and identify the person. Yeah, and also, for example, face restoration or restoration in general can be used in medical imaging. In general, we have to differentiate between two fields of face restoration, namely image FR and video FR. The field of image FR is quite well explored already, and there have been many methods developed for this, but the corresponding results for video FR still seem to be kind of missing. And this is mainly due to two types of reasons. First, reasons associated to the additional temporal dimension we have in video FR, so simply the fact that in videos we deal with moving images. This, first of all, requires a certain frame-to-frame consistency. Namely, when you restore a video, you cannot have in one frame one image and then in the next frame a completely different image. This would not be natural. You need a certain form of continuity in a video. Yeah, but also you have issues directly related to the motion, such as, for example, blurring, or you could also have changing lighting conditions. And the second type of reason why video FR seems to be so much harder is simply that we have a limited availability only of training data. So it's simply true that high quality annotated video data sets are pretty rare. And this, of course, also makes it more difficult to build robust models. And now this is the point where the present article comes into play, because this article tries to address some of these issues by introducing a new framework called Stable Video Face Restoration, or short SVFR. And something special about this SVFR framework is that it's not designed only for one specific face restoration subtask, but actually for three subtasks at once. These three tasks are listed here. The first one is just blind face restoration. So there you have some degraded or low quality image of a human face, and you try to enhance and recover the details. The second task is colorization, where you start with a black and white or grayscale image and you try to add back some realistic colors to the image. This, for example, I think is also something which most of us have already seen. For example, this is popular sometimes on YouTube, where you have these videos of very old footage from like the 1920s and they are recolorized. So this is exactly this. And the last task considered in SVFR is inpainting, where you have images with damaged or even completely missing parts, and you try to predict and reconstruct these lost parts. To make this a little bit more clear, we can also have a look at this image here taken from the article, where we see all these three tasks in action. So on the top, we have the blind face restoration. One starts with a kind of very blurry image, and then a specific model, here PGT former, is applied to reproduce this model in higher quality. And yeah, it seems to do a quite good job already. Then on the second line, we have the colorization task. So we start with a grayscale image and try to add back some realistic colors to the image. And finally, on the last line, we have the inpainting task where some white color has been painted over parts of an image, and these missing parts are then reconstructed here. And yeah, on this left-hand side, we see that all these three different tasks are carried out by separate models. And as I already said, something special about this new SVFR model is that it unites all these three subtasks into just one single model, which is capable of carrying out all these subtasks then. And the idea behind this is that actually the model might perform better in each individual subtask if it is trained on all three of the subtasks instead of only on one of the subtasks. And this is already kind of indicated in the image here. For example, if you look at the colorization task, then here where it's carried out by the so-called GPAN model, we see that there occurs some kind of unnatural orange color on the shirt of this guy. But the same problem does not occur when the same task is carried out here on the right-hand side by the SVFR model. And yeah, similarly also in the blind face restoration task, we can see when carried out by the PGT former model, this leads to a kind of little bit unnatural right eye of this person here. But when SVFR carries out the same task, again, this problem does not occur. So yeah, this just as a general motivation why SVFR might be a pretty good model. Now, the first thing which is actually done in the article is they carried out a pilot study to investigate if it's really true that a model can perform better in each individual subtask when it's trained on all three subtasks instead of only on one of them. And yeah, for the pilot study, this GPAN model was used. GPAN is actually an image face restoration model, but it can also be used for video face restoration simply by applying it frame by frame. And yeah, this GPAN model was then first pre-trained on one of the three subtasks, and subsequently it was trained on the remaining two subtasks. And the results achieved by this model were then compared to the results of essentially the same model, but without the pre-training. And yeah, for the evaluation here, the Frechet inception distance metric was used. And yeah, it really turned out that the pre-trained model always performed slightly better than the model that had not been pre-trained. And this really gave the motivation to build this new SVFR model in which these three subtasks are united. So next, let's have a look at the methodology and the modules used in this SVFR framework. So let me first give a brief overview over everything, and in the later slides, we will go into details. So first of all, as a base model, SVFR uses the so-called Stable Video Diffusion model, or short SVD. And then I would say SVFR contains two key aspects. The first key aspect is what we have already discussed, namely that it unites three different subtasks and allows these subtasks to mutually enhance their performances. This is done in the so-called Unified Phase Restoration Framework, which is composed of two modules. First, task embedding, and second, Unified Latent Regularization. And the second key aspect of SVFR is its focus on consistency. Namely, it further incorporates two more modules which guarantee both temporal consistency and also spatial coherence. And these two further modules are called facial prior learning and self-referred refinement. Good. Now that we've seen the overview, let's talk about the details. And let's start again with the base model, which, as I've already said, is the Stable Video Diffusion, or SVD model. Diffusion models in general can be used for both generation and reconstruction tasks. And typically they are trained in two steps, namely a forward process and a backward process. So one starts with the forward process, where one is given a real image, or in our case video, and then some randomly generated noise is gradually added to this video. After this, one proceeds with the backward process, where we now have a neural network. And this neural network is now trained to predict and remove this generated noise again, step by step. Then let's also have a look at how this SVD model actually does its work. So obviously one starts with an input video, here x, in Rn times 3 times h times w, where n denotes the number of frames, 3 is the number of color channels, h and w are height and width. And at the beginning, this input video is first encoded frame by frame into a latent space epsilon of x. Latent space essentially just means a different representation of the video, which will later be a little bit computationally more efficient. And yeah, after the encoding, the video is then passed to a so-called UNet. The UNet consists again of two different parts, a contracting path and an extending path. First, one uses the contracting path. Here, the size of the input video is stepwise decreased, and during this process, important features are extracted. And then when the minimum size of the video is achieved, one continues with the extending path, where we kind of go backwards again, because from then on again, the size of the video is gradually increased, and during this process, the details of the video are brought back. And after this whole procedure, the resulting video then just needs to be decoded back from its latent space representation into its original raw pixel representation. And yeah, the result from this will then be the final output of the model. And yeah, here we further see the loss function used for the training of Stable Video Diffusion, where epsilon denotes the randomly generated noise, and epsilon theta is the neural network used to predict this noise. And so essentially this loss function here can be understood as a variance of the noise when this generated noise epsilon is considered as the expected value. Good. So this summarizes the base model used in SVFR. Then next, let's continue with the first actual module constructed here for SVFR. That module is the so-called task embedding module. So yeah, the problem here is that several of the subtasks in the SVFR framework can potentially involve similar types of visual degradation. So for example, the problem of missing color information can be a problem in both the inpainting task and also the colorization task. And yeah, for this reason, the model might actually have difficulties to recognize the necessary restoration task for any given degraded input video. And so this task embedding module is constructed to help the model to correctly identify the necessary video restoration tasks and to adapt to these tasks. In this procedure, each of the subtasks is described by a binary indicator. 0 is used if the task is not necessary, sorry, and 1 is used if the task is actually necessary. And yeah, so this gives us a so-called task prompt vector consisting of 3 different values, all either 0 or 1. So for example, here in this 0, 1, 1, this means that we have a video which requires no blind phase restoration, but which requires both the colorization and the inpainting task. This task prompt vector is then passed to a task embedding layer, which in turn maps the prompt vector to a so-called task embedding. And this task embedding is then something that can be fed to the UNet of the SVD model to help the model to adapt to the specific task at hand. Okay, then the next important module in SVFR, this is the Unified Latent Regularization module, or short ULR. And this is actually very important because this is now really the module which allows the model to unify the 3 subtasks and allows these 3 subtasks to benefit each other. So more specifically, this ULR module teaches the model to extract so-called unified features, which means features that are not only relevant for one of the 3 subtasks, but for all 3 subtasks. And to achieve this, one takes the intermediate features extracted in the middle block of the UNet of the SVD model, and one first passes them through a so-called latent transformer, which consists of 2 residual blocks and a layer norm. And the output of this is then denoted by xi hat and passed to this regularizing term in the loss function. So what we have here is the negative logarithmic function of the exponential function of these extracted features xi hat times xi hat plus. And xi hat plus stand for features extracted from the same video but for a different subtask. And this is then divided by the sum over all videos in the batch of the exponential function of, again, the extracted features xi hat times xj hat minus. And xj hat minus here now denotes features extracted from a different video in the batch, but for the same task. And yeah, further tau here denotes a scaling parameter. And yeah, this looks a little bit ugly, but yeah, what we have to take from this is essentially simply that this part of the loss function will become small once the model has learned to extract similar features from one video for all three different subtasks. Okay, so this summarizes the ULR module, which is the module that teaches the model to unify the three subtasks. And then the next module we can have a look at is facial prior learning. So here the problem is that the base model, this SVD model, at first does not have any knowledge about realistic facial details and proportions. And therefore, the SVD model cannot be expected to generate images with these properties. So for this reason, the authors decided to integrate another objective function, which is supposed to really incorporate prior knowledge about human facial structures into the SVFR model. So more specifically, to this end, a pre-trained so-called landmark predictor is used, consisting of an average pooling layer and 5 multi-layer perception layers. And this landmark predictor is then trained to estimate 68 facial landmark points. So it learns, for example, where a nose is supposed to be in a human face, where the eyes are supposed to be, where the mouth is supposed to be, and so on. And yeah, for the training of this landmark predictor, a so-called facial prior loss function is applied, which is designed in such a way to really bring the predicted features, the predicted landmarks by the model closer to the actual ground truth landmarks. And yeah, this prior loss function looks like this. So here x denotes the difference or the error between the predicted landmarks and the actual ground truth landmarks. W and epsilon are simply some scaling parameters. And yeah, we can notice that this loss function is split into a logarithmic part when the error is small and a linear part when the error is large. And yeah, the constant c here is just used to guarantee continuity between the logarithmic and the linear part. And yeah, we can notice that in this loss function, larger errors are punished quite harshly thanks to the linear part, while at the same time, smaller errors will not be overpenalized thanks to the logarithmic part. Okay. Then there remains one more module to discuss, which is self-referred refinement. This module is introduced to the SVFR framework in order to guarantee temporal consistency, in particular along or across long video segments. And the problem or the reason why this needs to be introduced is indicated in the image down here, again taken from the article, where we see 3 different frames from the same video. And we see that in the latter 2 frames in the video, the head here is restored in a yellow color, but in this earlier frame here, the head has more of a bluish or greenish color. And yeah, this is bad, of course, because obviously this head did not just magically change its color throughout the video. But yeah, this is really a mistake caused by whatever model was used for the colorization task here. And yeah, so this self-referred refinement module is introduced to the SVFR model in order to prevent things like this from happening. And the idea of how this works is that it takes so-called reference frames, which can be injected into the generation process and to which the model can then compare its actual own predicted frames. In the training, this is pretty easy because for the reference frames, one can simply use frames from the actual ground truth video. And also during the training period, 50% dropout rate is applied to the reference frames in order to improve the generalization and teach the model to also restorate videos consistently even without any explicit references given. But during the inference mode, it's a little bit more difficult because there, of course, we do not have a ground truth video given from which we could take any reference frames. So one has to proceed in a different way. And what one does is one first restaurates a small segment of the video without relying on any reference. But then from this first restored segment, one can take one frame and use that frame as a reference frame for the restoration of the later segments in the video. Okay. Now, this was the last of the modules in SVFR. So now we have seen the whole methodology. And now that we kind of understand how the model works, we can have a look at the actual evaluation. So in the article, the SVFR model was evaluated on 3 different data sets, all of which had been manually degraded. And yeah, the data sets were VoxCeleb2, CelebV text, and VFHQ. I don't actually know too much about them, but these are the names. And yeah, for the metrics, they used metrics on both the image and the video level. So on the image level, for example, they had PSNR and SSIM, which evaluate reconstruction accuracy on individual frames. LPIPS to evaluate the perceptual quality, and also the consistency in phase restoration was assessed using the IDS metric. Then on the video level, they had the VIDD metric, which is used to evaluate the temporal consistency by calculating identity feature differences between subsequent frames. And further, they had the FVD metric in order to evaluate the overall video quality with a specific focus on spatial and temporal coherence. Then there were several state-of-the-art baseline models to which SVFR was compared in the article. First of all, image-based models, which can be used to restore videos frame by frame, such as GPen, CodeFormer, and PGDiff, but also video-based models, which were created specifically to restore videos, such as PGTFormer or Keep. And yeah, I won't go into detail here. I won't show any tables or numbers. I think this would be a little bit too much for a short presentation. But yeah, of course, if you're interested, you can check them out for yourselves in the article. Yeah, let me just briefly mention that in the article, SVFR was really shown to consistently outperform the models stated here in various benchmark tests across all the datasets and metrics which we have seen on the previous slide. Then the article also provides some visual examples for how these models are evaluated. And here I would like to show one specific example, which I think is quite interesting, namely what we see here. This is really an evaluation of the temporal consistency of the restored models. So what is going on here is one takes from each frame of a given image a vertical stack of pixels like this. And then these vertical stacks are aligned horizontally next to each other, which leads to these kind of very blurry looking images. And yeah, from these images, we can then really see if the restored video is actually continuous in time. And if we look at the results achieved down here by the SVFR model and compare this in particular to the results achieved by the image FR models, which were GPen, CodeFormer, and PGDiff, then we really see that SVFR looks quite a lot smoother because it has less jitter and less misalignment. And this kind of visually indicates that really that really the model, the SVFR model, is capable of achieving a stronger temporal consistency than other models, and in particular the image-based models. Okay. And then the last thing I would like to talk about are the ablation studies carried out in the article. So ablation study essentially means studies where the model is evaluated with individual modules excluded. This is done to evaluate the contribution of individual modules on the overall performance of the model. So here, first of all, of course, the multitask training is evaluated. So this is similar to the pilot study we had discussed earlier. And yeah, it was really shown that the model performs better in each individual subtask if it is trained on all three subtasks together instead of only on one of them. And yeah, further ablation studies also showed that the ULR, or Unified Latent Regularization module, improves the consistency across different tasks, with in particular positive impact on video clarity, facial details, and even temporal stability. Also, the facial prior learning module was seen to enhance the spatial coherence and also the temporal consistency. And finally, the self-referred refinement module was in particular seen to improve the temporal consistency in or across long segments of videos. Good. Now that's all essentially I can say. So let me just briefly conclude. So in the present article, or the article we just discussed, the SVFR framework was introduced, which is a video face restoration framework that unites three different general FR tasks into one single model, namely blind face restoration, colorization, and inpainting. Also, the SVFR framework makes use of two more modules that guarantee temporal consistency and spatial coherence. In the experimental results carried out in the article, we saw that SVFR is able to consistently outperform other leading models across various benchmark tests. And finally, it was also seen that the three subtasks used in SVFR really mutually enhance each other's performance. Yes, so this is really everything now. And so thank you for your attention.